The story of a star's final breath. Every star has a life, a beginning, a middle, and an end. For the most massive stars, those born with 8 times the sun's mass or more, the ending is spectacular. They burn through their fuel quickly, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, building up layers like an onion. But fusion can only go so far. When the core turns to iron, the process stops. Iron doesn't release energy when it fuses. It consumes it, and without the outward pressure from fusion to balance gravity's inward pull, the core collapses. In less than a second, the core implodes, crushing matter to densities beyond comprehension. The outer layers rebound in a catastrophic explosion, a supernova. And at the center, if the core isn't too massive, what remains is a neutron star. It's the final breath of a giant, the last gasp before silence, or rather, before a new kind of existence begins. A star's death becomes something else entirely, something small, dense, and endlessly fascinating. The end of a massive life. Massive stars live fast and die young. While our sun will burn for about 10 billion years, a star 20 times more massive might last only a few million years. They're cosmic fireworks, brilliant and brief. During their lives, these giants shine with incredible luminosity, fusing elements in their cores at furious rates. But this intensity comes at a cost. The fuel runs out quickly, and when it does, the end comes suddenly. The core collapses, the star explodes, and in that violent moment, the star's legacy is split. The outer layers are scattered into space, enriching the cosmos with heavy elements, carbon, oxygen, iron, all forged in the star's core or in the explosion itself. But the inner core remains, crushed by gravity into a ball of neutrons. This is the end of a massive life, but it's also a transformation. The star doesn't disappear. It becomes something new, something strange, a neutron star, a monument to the power of gravity and the resilience of matter under extreme conditions. The birth of a neutron star. When the core collapses, electrons and protons are crushed together, merging into neutrons through a process called neutronization. In a fraction of a second, a core the size of Earth compresses into a sphere just 20 kilometers across. That's about the size of a city. The density becomes so extreme that a sugar cube-sized amount of this matter would weigh as much as a mountain. This is the birth of a neutron star, a moment of incredible violence, giving rise to one of the universe's most exotic objects. The newborn star is unimaginably hot, around 1 trillion degrees, glowing with neutrinos that carry away most of the supernova's energy. It's also spinning rapidly, inheriting the angular momentum of the collapsing core, and it's wrapped in a magnetic field billions of times stronger than anything on Earth. This birth is quick, brutal, and transformative. What was once the core of a giant star is now a cosmic relic, a laboratory for physics at its most extreme. The death of a giant sun. Not every star becomes a neutron star. Our sun won't. When it dies, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a hot, dense ember, slowly cooling over billions of years. But stars much more massive than the sun meet a different fate. They burn hotter, fuse heavier elements, and when they run out of fuel, they don't fade quietly. They explode. The death of a giant sun is a supernova, one of the brightest events in the universe. For a few weeks, a single dying star can outshine an entire galaxy. And at the heart of that explosion, if the core is massive enough, but not too massive, a neutron star is born. If the core is even heavier, it collapses further, becoming a black hole. But in that narrow range, between about 1.4 and 2.5 solar masses, the core stabilizes as a neutron star. The death of a giant sun is the beginning of a neutron star's story, the supernova that creates a core. The supernova is the crucible. It's the event that both destroys the star and creates the neutron star. When the core collapses, it rebounds, sending a shock wave outward through the star's layers. This shock wave rips the star apart, ejecting most of its mass into space at thousands of kilometers per second. The explosion is so energetic that it synthesizes new elements, creating atoms heavier than iron in the intense heat and pressure. Gold, platinum, uranium. These elements are forged in supernovae and neutron star collisions, scattered into space to become part of future planets and perhaps even living beings. But at the center, the core remains, compressed to the point where atomic structure breaks down, where neutrons are packed together in a state of matter that doesn't exist anywhere else in the universe. The supernova creates chaos, but it also creates a core, a neutron star, the densest object short of a black hole. The collapse that defies imagination. Try to imagine the collapse. A core roughly the size of Earth, containing more mass than the Sun, imploding in less than a second. The speeds involved are almost a quarter of the speed of light. The forces are incomprehensible. Atoms are crushed out of existence. Electrons and protons merge into neutrons. The temperature soars to trillions of degrees. And all of this happens in a heartbeat. It's a collapse that defies imagination, because nothing in our everyday experience comes close. We can describe it with numbers, with equations, but truly understanding what happens requires accepting that the universe operates on scales and in ways that our minds weren't evolved to grasp. The collapse is the most extreme event a star can undergo without becoming a black hole. It's the point where matter is pushed to its absolute limit, where the fundamental forces of nature battle for dominance. And somehow, in that battle, a neutron star emerges, stable, spinning, and impossibly dense. The force stronger than atoms. What stops the collapse? Why doesn't the core keep shrinking into a black hole? The answer is a quantum force called neutron degeneracy pressure. In normal matter, atoms have structure. Electrons orbit nuclei, separated by mostly empty space. But when you crush matter hard enough, that structure breaks down. Electrons merge with protons, forming neutrons, and neutrons, like electrons, obey the Pauli exclusion principle, a quantum rule that says two identical particles can't occupy the same quantum state. When neutrons are packed tightly, this principle creates a pressure, a resistance to further compression. It's not a force in the traditional sense. It's a consequence of quantum mechanics, and it's strong enough to halt the collapse of a stellar core, to balance the crushing weight of gravity. The force stronger than atoms is what makes neutron stars possible, what prevents them from collapsing into black holes. It's nature's last line of defense against total gravitational victory. The core that refused to die. In a way, a neutron star is a core that refused to die. When the rest of the star exploded, scattering into the cosmos, the core remained. It couldn't sustain fusion anymore. There's no nuclear burning in a neutron star, but it didn't disappear either. It found a new equilibrium, a balance between gravity trying to crush it and quantum pressure pushing back. This core is no longer a star in the traditional sense. It's not generating energy through fusion. It's not shining with its own light, except for the residual heat from its violent birth. But it's still there, still massive, still exerting its gravitational pull on the space around it. The core that refused to die is a monument to the extremes of physics, a reminder that even in the face of catastrophic destruction, matter can find a way to persist, to stabilize, to exist in forms we're only beginning to understand. The smallest and densest stars in the universe, neutron stars, hold a title. They're the smallest and densest stars in the universe. Black holes are denser, but they're not stars. They're singularities, points where the laws of physics break down. Neutron stars are objects we can still describe with physics, even if that physics is stretched to its limits. With diameters of just 20 to 25 kilometers, They're tiny compared to regular stars. Our sun is 1.4 million kilometers across. A neutron star would fit inside a large city, yet they contain more mass than the sun. All of that matter is compressed into a sphere so dense that a single teaspoon of neutron star material would weigh about 1 billion tons. That's more than all the cars on Earth combined. The smallest and densest stars in the universe are laboratories where we can study matter in conditions we can never replicate on Earth. They're natural experiments, showing us what happens when gravity wins almost completely. The star crushed into a city size. Imagine a star the size of a city, not spread out like the sun, but compressed. Every bit of its mass squeezed into a sphere you could drive across in half an hour. That's a neutron star. From the surface to the center, it's only about 10 kilometers. And yet within that tiny volume, there's more mass than in our entire sun. The star crushed into a city's size is a marvel of extremes. Its surface gravity is about 2 billion times stronger than Earth's. If you could somehow stand on a neutron star, which you couldn't, you'd be instantly crushed. You'd weigh billions of times more than you do now. A single step would require the energy output of a rocket. The escape velocity is about half the speed of light, and the landscape, if you could see it, would be strange beyond words. Mountains just millimeters tall, because gravity won't allow anything higher. A smooth, crystalline surface, harder than any material we know. The weight of the sun in a teaspoon. The density of a neutron star is almost beyond comprehension. A teaspoon of neutron star material would weigh about 1 billion tons. That's roughly the weight of Mount Everest in a teaspoon. To put it another way, if you could somehow bring a teaspoon of this matter to Earth, its gravity would be so strong that it would pull everything around it inward, likely boring through the planet's crust under its own weight. The weight of the sun in a teaspoon is a metaphor, but it's close to reality. A neutron star's entire mass, equivalent to our sun or more, is packed into a volume smaller than most cities. This density is achieved by crushing atomic structure entirely. There are no atoms in the traditional sense, just neutrons pressed together as tightly as quantum mechanics allows. It's matter at the edge of what's possible, a state so extreme we can barely simulate it with our most powerful computers. The gravity that bends all around it. Near a neutron star, gravity warps everything. Space and time bend. Light curves, and the very fabric of the universe distorts into strange geometries. This is general relativity in action. Einstein's prediction that mass bends spacetime, and neutron stars, with their extreme density, bend it severely. If you could observe a neutron star from up close, you'd see bizarre optical effects. Light from the far side of the star would bend around it, allowing you to see more than half of its surface at once. Time would run slower near the surface than farther away, a phenomenon called gravitational time dilation. And if you were falling toward the star, you'd experience tidal forces strong enough to stretch and compress you. Spaghettification, as it's sometimes called. The gravity that bends all around a neutron star is a reminder that these objects aren't just dense, they're distortions in the cosmos itself, regions where the normal rules are rewritten by the sheer concentration of mass. The pressure beyond nuclear strength. Inside a neutron star, the pressure is unimaginable. At the core, it's estimated to be quadrillions of times greater than atmospheric pressure on Earth. This pressure is beyond anything we can create in laboratories. It's beyond the pressure at the center of atomic nuclei. At these extremes, we're not entirely sure what matter becomes. Neutrons might break down into quarks, the fundamental particles that make up protons and neutrons. The core might be a quark soup, or it might contain exotic particles we've never observed. The equations that describe nuclear physics start to break down because we've never tested them at these pressures. The pressure beyond nuclear strength is one of the great unknowns in astrophysics. Neutron stars are the universe's laboratories for extreme matter, And they're showing us states of existence that challenge our deepest theories about how matter works at the most fundamental level. The neutrons packed like a crystal. In the outer layers of a neutron star, just below the surface, neutrons are packed so tightly, they form a kind of crystal. Not a crystal in the way we think of ice or diamonds, but a lattice of neutrons, arranged in a regular pattern, held in place by quantum forces. This neutron solid is incredibly stiff, far harder than any material on Earth. It's thought to be billions of times stronger than steel. And beneath this crust, the neutrons transition into a superfluid, a state where they flow without friction, where quantum effects dominate on macroscopic scales. The neutrons packed like a crystal form the rigid outer shell of the star, the structure that holds it together and allows it to support mountains, albeit tiny ones. This crystal lattice can crack during starquakes, sudden readjustments as the star's rotation slows. When it does, it releases enormous amounts of energy, sometimes detectable as glitches in the star's pulsing rhythm. The temperature of a newborn neutron star. When a neutron star is born, it's unimaginably hot. The core reaches temperatures around 1,000,000,000 degrees Celsius, hotter than any furnace, hotter than the heart of any normal star. At these temperatures, the star glows intensely, though most of the energy is carried away by neutrinos, ghostly particles that barely interact with matter. Over time, the neutron star cools. It radiates thermal energy into space, its surface temperature dropping from millions of degrees to tens of thousands, then eventually to cooler temperatures over millions of years. The temperature of a newborn neutron star is a product of the violent collapse that created it, the gravitational energy converted into heat. But unlike regular stars, which maintain their temperature through fusion, neutron stars are born hot and then cool down. They're like embers from a cosmic fire, slowly losing their heat to the cold void of space. The cooling that takes millions of years. A neutron star doesn't cool quickly. The process takes millions, even billions of years. Initially, the cooling is rapid, driven by neutrino emission from the hot core. Neutrinos escape easily, carrying energy away. But as the core temperature drops, neutrino emission decreases, and the cooling slows. Eventually, the star cools primarily through photon emission from its surface, a much slower process. By the time a neutron star is a few million years old, its surface temperature might have dropped to around 1,000,000 degrees, still incredibly hot by our standards, but much cooler than at birth. The cooling that takes millions of years is gradual, almost gentle, a long fade from intense heat into relative coolness. Old neutron stars, billions of years old, might have surface temperatures just a few thousand degrees, barely glowing, nearly invisible, but they're still there, still dense, still exerting their gravitational influence, now just cold and dark. The crust harder than diamond. The crust of a neutron star is the hardest substance in the universe. It's composed of atomic nuclei and electrons, but under such extreme pressure that the nuclei are packed into a crystal lattice, far denser and stronger than anything found on Earth. Diamond is the hardest natural material we know, but it's nothing compared to neutron star crust. The crust is estimated to be 10 billion times stronger than steel. It has to be. It's supporting immense pressure from the layers below, holding the star's structure together against gravity's relentless pull. This crust is only about 1 kilometer thick, but within that thin shell lies material in a state we can barely imagine. Below the crust, the neutrons transition into a superfluid and deeper still, possibly into quark matter. The crust harder than diamond is the star's protective shell, the barrier between the weird quantum fluids inside and the vacuum of space outside. The surface smooth as a mirror. The surface of a neutron star is extraordinarily smooth. Gravity is so strong that it crushes any irregularities. Mountains on a neutron star can only be millimeters tall before gravity flattens them. The surface is thought to be crystalline, a lattice of iron nuclei in the outer layers, forming a solid crust, and it's smooth. Smoother than a billiard ball, smoother than anything we can manufacture. If you could run your hand over it, which you absolutely couldn't, without being instantly vaporized and crushed, it would feel almost perfectly flat. The surface, smooth as a mirror, is a consequence of extreme gravity. Nothing can stand tall. Nothing can protrude. The star's shape is nearly a perfect sphere, perhaps slightly flattened by rapid rotation, but otherwise featureless. This smoothness is eerie, a landscape without variation, a cosmic ball of matter polished by gravity's inexorable hand. The magnetic fields that defy belief. Neutron stars have magnetic fields trillions of times stronger than Earth's. These fields are so intense they can distort atoms, aligning electron orbits, creating effects we never see in everyday life. A typical neutron star's magnetic field might be around 1 trillion Gauss. For comparison, Earth's magnetic field is about half a Gauss. A refrigerator magnet is maybe 100 Gauss. 1 trillion Gauss is an environment where quantum electrodynamics, the physics of how light and matter interact, starts behaving strangely. Light can split into different polarizations. Vacuum itself can be affected. And in some neutron stars, the magnetic fields are even stronger. The magnetic fields that defy belief are created during the star's formation, as the collapsing core concentrates the original star's magnetic field into a much smaller volume. Conservation of magnetic flux means the field strength increases dramatically, and once established, these fields decay only slowly, persisting for millions of years, shaping the star's behavior and its interaction with the surrounding space. The magnetar, a neutron star on fire. Among neutron stars, there's a special class called magnetars. These are neutron stars with magnetic fields so intense they make ordinary neutron stars look weak. Magnetar fields can reach quadrillions of Gauss, 1,000 times stronger than typical neutron stars. At these strengths, the magnetic field itself becomes a dominant force, capable of cracking the star's crust, generating powerful starquakes, and producing enormous eruptions of X-rays and gamma rays. Magnetars are rare, perhaps only a few dozen in our galaxy, but they're among the most violent objects known. When a magnetar flares, it can release more energy in 1/10 of a second than the sun emits in a year. The magnetar, a neutron star on fire, isn't actually burning. There's no combustion, but the magnetic energy is so immense that it drives explosive events, lighting up the star in high-energy radiation, making it visible across the galaxy, despite its tiny size. The fields that tear atoms apart. In the vicinity of a magnetar, magnetic fields are strong enough to distort and even tear atoms apart. Normally, atoms are held together by electromagnetic forces, with electrons orbiting nuclei in specific energy levels. But in fields of 1 quadrillion Gauss, these energy levels shift and distort. Atoms become elongated, stretched by the magnetic force. Chemistry as we know it breaks down. The fields that tear atoms apart are difficult to study because we can't recreate them on Earth. Our strongest laboratory magnets reach maybe tens of millions of Gauss, nowhere near magnetar strength, so we rely on observations and theoretical models. These fields affect how the star's surface radiates light, how particles move in its magnetosphere, and how energy is released during flares. The magnetic forces are so strong they can stress the star's crust, causing it to crack and shift, releasing enormous bursts of energy. It's a realm where magnetism reigns supreme, shaping everything. The energy of 1 trillion Gauss. 1 trillion Gauss. It's hard to comprehend what that means. Earth's magnetic field protects us from solar wind, guides compasses, and enables the auroras. It's about half a Gauss. Hospital MRI machines use fields of a few Tesla, tens of thousands of Gauss. The strongest sustained magnetic fields created in laboratories reach perhaps 45 Tesla, or 450,000 Gauss. A neutron star's field is a trillion Gauss. At that strength, the magnetic field has pressure. It can exert forces strong enough to shape the star's structure, accelerate particles to near light speed, and generate radiation across the spectrum. The energy of a trillion Gauss is stored in the field itself, and as the field evolves and decays over time, that energy is released, powering the star's emissions. For magnetars, with even stronger fields, the energy is proportionally greater, capable of producing some of the most powerful explosions in the universe. The magnetic field becomes a reservoir of energy, slowly leaking out over millennia. The explosions of magnetar flares. Magnetars occasionally erupt in spectacular flares. These aren't nuclear explosions. There's no fusion happening. They're magnetic explosions, caused by sudden rearrangements of the star's incredibly strong magnetic field. When the field twists and reconnects, it releases enormous amounts of energy instantaneously. The largest magnetar flares ever observed have brightened the star by factors of thousands or even millions in a fraction of a second, releasing energy equivalent to what the sun emits in decades. These flares send out bursts of X-rays and gamma rays, flooding the surrounding space with high-energy radiation. If a magnetar flare occurred close to Earth, within a few light years, it could pose a serious threat, potentially damaging our atmosphere and technology. Fortunately, the nearest known magnetar is much farther away. The explosions of magnetar flares are among the most energetic transient events in the universe, brief but incredibly powerful, showcasing the extreme physics at play in these strange stars. The light bursts that reach across the galaxy. When a magnetar flares, its light can reach across the galaxy. These bursts of X-rays and gamma rays travel at the speed of light, spreading outward in all directions. Telescopes across the solar system and beyond can detect them, sometimes recording the flare as a sudden, intense spike in high-energy radiation. The light bursts aren't uniform. They're often structured, with the initial spike followed by a tail of gradually decreasing emission as the star's surface settles back down. Astronomers study these bursts to learn about the magnetar's magnetic field, its crust dynamics, and the processes that trigger the flare. The light bursts that reach across the galaxy are messengers, carrying information about events happening on the surface of a star just 20 kilometers across, thousands or tens of thousands of light years away. Despite the vast distance, the intensity of the flares makes them detectable, allowing us to witness the extreme behavior of these remarkable objects. The radio pulses of a rotating star. Many neutron stars are pulsars, emitting beams of radio waves from their magnetic poles. As the star rotates, these beams sweep through space like lighthouse beams. If a beam happens to point toward Earth, we detect a pulse of radio emission. Then, as the star continues to rotate, the beam sweeps away, and we see nothing until it comes around again. This creates a regular pattern of pulses, ticking with incredible precision. The radio pulses of a rotating star are generated in the star's magnetosphere, the region around it filled with charged particles, accelerated by the magnetic field. These particles emit radiation as they spiral along magnetic field lines, concentrated into narrow beams. The exact mechanism isn't fully understood, but the result is clear: a pulsing radio signal, as regular as any clock, broadcast across the cosmos. These pulses allow us to study neutron stars from great distances, measuring their rotation, magnetic field, and even their position in space with remarkable accuracy. The discovery of the first pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University. She was analyzing radio telescope data when she noticed an unusual signal, a series of regular pulses, occurring precisely every 1.337 seconds. At first, the regularity was so striking that some joked it might be a signal from an alien civilization, playfully dubbed LGM-1 for little green men, but further observations revealed more pulsars, each with its own period, and it became clear these were natural phenomena. The discovery of the first pulsar was a watershed moment in astronomy. It confirmed the existence of neutron stars, objects that had been theorized but never observed. It opened up a new field of research, pulsar astronomy, which has since yielded profound insights into physics, from testing general relativity to detecting gravitational waves. Jocelyn Bell Burnell's discovery, made with careful observation and persistence, changed our understanding of the universe. Remarkably, she was not included in the Nobel Prize, later awarded for the discovery, a controversial decision that remains a topic of discussion in scientific circles. The beacons of the universe. Pulsars are often called the beacons of the universe. They're cosmic lighthouses, sending out regular pulses that sweep across space. These beacons are incredibly useful for astronomy because pulsars pulse with such regularity. They can be used as precise clocks. Millisecond pulsars, in particular, rival the best atomic clocks on Earth. In their timing precision, astronomers use pulsars to test theories of gravity, to map the distribution of matter in the galaxy, and even to search for gravitational waves. Arrays of pulsars spread across the sky act as a galaxy-wide gravitational wave detector, sensitive to ripples in space-time from supermassive black hole mergers. The beacons of the universe are also navigational aids. In the 1970s, the Pioneer and Voyager spacecraft carried plaques showing Earth's location relative to nearby pulsars, a cosmic map for any intelligence that might find them. Pulsars, with their steady ticking, are not just objects of study. They're tools, references, and symbols of the universe's clockwork precision. The precision of their cosmic ticking. Pulsars tick with extraordinary precision. The best millisecond pulsars have periods stable to 1 part in 10 billion over a year. That's more precise than the best atomic clocks. This precision arises because the pulsar's rotation is governed by simple physics, angular momentum conservation, and isn't subject to the kinds of disturbances that affect human-made clocks. The precision of their cosmic ticking makes pulsars invaluable for science. Tiny deviations in pulse timing can reveal the presence of planets orbiting the pulsar, the passage of gravitational waves, or changes in the interstellar medium between us and the pulsar. Timing arrays monitor dozens of millisecond pulsars simultaneously, looking for correlated deviations that would signal gravitational waves from distant supermassive black holes. The precision is so high that we can detect changes measured in nanoseconds, billionths of a second, across years of observation. Pulsars are nature's clocks, and they're among the most accurate timekeepers in the cosmos. The clockwork of the cosmos. There's something deeply satisfying about the regularity of pulsars. In a universe that often seems chaotic, where stars explode and galaxies collide, pulsars offer a sense of order. They tick with metronomic regularity, their pulses arriving like clockwork. This regularity is a product of physics. A spinning neutron star is an incredibly stable rotator. Its moment of inertia is enormous, and there's almost no friction in space to slow it down, except for the energy it radiates. So it spins, and spins and spins, slowing only gradually over millions of years. The clockwork of the cosmos, embodied in pulsars, reminds us that beneath the apparent chaos, there are fundamental laws that govern everything. These stars, born in violence, have become the universe's most reliable timekeepers. They're living demonstrations of conservation laws, of the deep mathematical order underlying reality. And in their steady ticking, there's a kind of cosmic reassurance, a rhythm, a heartbeat, a reminder that the universe, for all its strangeness, operates by rules we can understand. The twin beams that sweep the sky. A pulsar's radio emission comes from 2 beams, one from each magnetic pole. These beams are like searchlights, narrow cones of radio waves sweeping through space as the star rotates. The beams don't necessarily point along the star's rotation axis. In fact, they usually don't. The magnetic axis is tilted relative to the rotation axis, much like Earth's magnetic and geographic poles don't align. This tilt is what creates the pulsar effect. As the star spins, the beams sweep around in circles. If one of those circles happens to intersect Earth, we see a pulse each time the beam points our way. The twin beams that sweep the sky are generated in the pulsar's magnetosphere, where charged particles are accelerated to high energies. The exact mechanism is complex, involving electromagnetic cascades and plasma physics, but the result is these focused beams of radiation, marking the pulsar's presence across the galaxy. The rhythm of the pulsar heartbeat. Each pulsar has its own rhythm, its own heartbeat. Some pulse slowly, once per second, or even slower. Others pulse rapidly, dozens or even hundreds of times per second. The rhythm depends on the pulsar's rotation rate, which in turn depends on its age, mass, and history. Young pulsars, born in recent supernovae, tend to spin faster and slow down over time as they lose energy. Old pulsars, unless they've been spun up by accreting matter from a companion star, spin more slowly. The rhythm of the pulsar heartbeat is personal to each star, a signature that identifies it. Astronomers catalog pulsars by their periods, positions, and other characteristics, building up a census of these objects across the galaxy. And in that rhythm, that steady pulse, there's something almost biological, as if the neutron star has a heartbeat, as if it's alive in some strange cosmic way. The millisecond pulsars, spinning at the edge of physics. Millisecond pulsars are the fastest spinning neutron stars, rotating hundreds of times per second. The fastest known millisecond pulsar, PSRJ 1748-2446 AD, spins at 716 times per second. That means its surface is moving at about a quarter of the speed of light. At this speed, the star is nearly tearing itself apart. The centrifugal force is enormous, counteracting gravity, slightly flattening the star into an oblate spheroid. Any faster, and the star would likely break apart, unable to hold itself together against the centrifugal strain. Millisecond pulsars, spinning at the edge of physics, are thought to have been spun up by accreting matter from a companion star. As matter falls onto the neutron star, it transfers angular momentum, speeding up the rotation. This process recycles old pulsars, giving them new energy and setting them spinning at these incredible rates. They're cosmic spinning tops, balanced on the edge of what's physically possible. The fastest rotation ever measured, 716 rotations per second. In the time it takes to blink, this pulsar has spun more than 100 times. The fastest rotation ever measured belongs to PSRJ 1748-2446 AD, a millisecond pulsar in a globular cluster. Measuring such rapid rotation requires sophisticated timing techniques. Analyzing the pulses with precision instruments, the rotation rate tells us about the star's structure and history. It also tests our theories. Can a neutron star spin this fast without breaking apart? What does this tell us about the strength of its crust, the distribution of mass, the limits of matter under extreme conditions? The fastest rotation ever measured pushes the boundaries of astrophysics. It shows us what neutron stars are capable of and raises questions we're still trying to answer. How fast can they spin? What's the ultimate limit? And what happens if they exceed it? These are questions that millisecond pulsars help us explore, one rapid pulse at a time. The energy released in each spin. Every time a pulsar spins, it releases energy, not from fusion. Neutron stars don't fuse atoms, but from their rotation. As the star spins, its magnetic field sweeps through space, accelerating charged particles, generating radiation. This process drains rotational energy, causing the pulsar to slow down over time. The energy released in each spin depends on the pulsar's rotation rate and magnetic field strength. For typical pulsars, it's a tiny amount per rotation, but multiplied by hundreds or thousands of rotations per second and sustained over millennia, it adds up. This energy powers the pulsar's radio beams, its magnetosphere, and in some cases, the surrounding pulsar wind nebula, a glowing cloud of high-energy particles. The energy comes from the star's spin down, the gradual loss of rotational kinetic energy. Eventually, after millions of years, the pulsar will spin too slowly and its radio emission will cease. It becomes a quiet neutron star, still there, still dense, but no longer pulsing. The strange timing of their signals. Pulsar signals can be strange. Most pulsars have remarkably stable periods, but occasionally they glitch, suddenly spinning up slightly, increasing their rotation rate in a fraction of a second. Then they gradually relax back, spinning down again over weeks or months. These glitches are thought to be caused by starquakes, cracks in the neutron star's crust, or sudden transfers of angular momentum from the superfluid interior to the crust. The strange timing of their signals also includes irregularities caused by the interstellar medium. Radio waves traveling through space are affected by free electrons, which cause dispersion. Lower frequencies arrive slightly later than higher frequencies. By measuring this dispersion, astronomers can estimate the distance to the pulsar and map the distribution of electrons in the galaxy. The timing is also affected by the pulsar's motion, by gravitational effects, if it's in a binary system, and by gravitational waves passing through our region of space. Every detail in the timing reveals something about the pulsar or its environment. The binary systems of neutron stars. Some neutron stars aren't alone. They're part of binary systems, orbiting a companion star or even another neutron star. These systems are laboratories for studying gravity, stellar evolution, and exotic physics. When a neutron star orbits a companion, their mutual gravity affects each other's motion. If the companion is another star, the neutron star can pull material from it, forming an accretion disk. This process can spin up the neutron star, turning it into a millisecond pulsar. If the companion is another neutron star, the system becomes incredibly interesting. Two dense objects orbiting each other, each warping space-time, creating gravitational waves that carry energy away from the system. The binary systems of neutron stars are diverse. Some pairs orbit closely, completing an orbit in hours. Others are widely separated, taking years to complete one revolution. By studying these systems, astronomers measure neutron star masses with precision, test general relativity in strong gravitational fields, and watch as the orbits decay, bringing the stars closer together. These binaries are cosmic laboratories, revealing physics we can't study any other way. The dance of two dead suns. Two neutron stars orbiting each other perform a gravitational dance. They're the remnants of two massive stars that once lived and died in the same system. Now they circle each other, bound by gravity, moving through space together. This dance is intimate and inevitable. As they orbit, they emit gravitational waves, ripples in space-time predicted by Einstein. These waves carry energy away from the system, causing the orbit to decay. The stars spiral closer, gradually at first, then faster as they approach. The dance of two dead suns is a slow-motion collision playing out over millions or billions of years. Eventually, the orbit becomes so tight that the stars are just kilometers apart, whipping around each other hundreds of times per second. And then, in the final moments, they merge. The collision is cataclysmic, releasing more energy in a second than the sun will emit in its entire lifetime. It's a dance that ends in destruction, but also in creation, forging new elements and lighting up the cosmos. The gravitational waves from their orbits. As binary neutron stars orbit, they disturb space-time itself, creating gravitational waves. These waves are like ripples on a pond, except the pond is the fabric of the universe. Einstein predicted them in 1916, but they weren't directly detected until 2015, when LIGO observed waves from merging black holes. In 2017, LIGO and Virgo detected gravitational waves from merging neutron stars for the first time. The waves arrived at Earth after traveling for 130 million years, carrying information about the masses, spins, and final moments of the colliding stars. The gravitational waves from their orbits are incredibly weak by the time they reach us. They stretch and compress space by less than the width of an atomic nucleus over several kilometers. But modern detectors are sensitive enough to measure these tiny distortions. By studying gravitational waves, astronomers can observe events that are invisible in light, opening a new window on the universe. Neutron-star mergers are particularly valuable because they produce both gravitational waves and light, allowing multi-messenger astronomy. The in-spiral that ends in a collision. The in-spiral is the final approach. Two neutron stars, having orbited each other for millions of years, are now just kilometers apart. Their orbital period has shortened from days to hours to minutes to fractions of a second. They're moving at a significant fraction of light speed, their gravitational waves growing stronger and stronger. The in-spiral that ends in a collision is brief but intense. In the last few seconds, the stars spiral around each other hundreds of times, the gravitational waves sweeping up in frequency like a cosmic chirp. Detectors on Earth record this chirp, capturing the moment when two stars become one. Then the collision. The stars merge in a violent event that deforms them, possibly tearing them apart before gravity reassembles the pieces. The result might be a more massive neutron star, or, if the combined mass exceeds about 2.5 solar masses, a black hole. The in-spiral tells us about the star's properties, testing our understanding of matter and gravity. The kilonova that lights the universe. When neutron stars merge, they create a kilonova, an explosion powered by radioactive decay of heavy elements. The merger ejects material, neutron-rich matter that undergoes rapid nuclear reactions, forming elements like gold, platinum, and uranium. This material is radioactive, and as it decays, it releases energy, heating the expanding cloud. The cloud glows, first in blue light, then shifting to red as it expands and cools. The kilonova that lights the universe is visible for days or weeks, a beacon announcing the merger. The 2017 event, named AT 2017 GFO, was observed by telescopes around the world in multiple wavelengths. It confirmed that neutron star mergers are the primary source of heavy elements in the universe. The kilonova was dimmer than a supernova, but still incredibly bright, easily visible across the universe with modern instruments. It showed us the birth of gold, the creation of elements that make up our technology, our jewelry, our world. Every atom of gold on Earth was likely forged in a neutron star collision billions of years ago. The gold created in a star's death. Gold doesn't come from stars like the sun. It's too heavy. Regular stellar fusion stops at iron. Elements heavier than iron require different processes, and one of the most important is the rapid neutron capture process, or RA process, which happens in neutron star mergers. When two neutron stars collide, the intense neutron flux allows rapid capture of neutrons by atomic nuclei, building up heavy elements in seconds. The gold created in a star's death is scattered into space by the kilonova, mixing with interstellar gas, eventually becoming part of new stars, planets, and perhaps life. Every gold ring, every gold coin, every piece of gold circuitry and electronics, all of it was created in the violent collision of neutron stars, somewhere in the universe, sometime in the past. It's stardust, literally. The gold we treasure is a remnant of cosmic cataclysm, a fragment of stellar death, carried across space and time to become part of our world. The heavy elements born from collisions. Gold is just one example. Neutron star mergers create many heavy elements: platinum, uranium, thorium, rare earth elements. These are the products of the R process, forged in the neutron-rich environment of the merger. Before the 2017 kilonova observation, astronomers suspected neutron star collisions were the source, but direct confirmation was lacking. The detection of heavy element signatures in the kilonova spectrum provided that confirmation. The heavy elements born from collisions are essential for technology, for medicine, for science. Uranium powers nuclear reactors and was used in early nuclear weapons. Rare earth elements are crucial for modern electronics. All of it traces back to neutron stars, to the collisions that seed the universe. With these atoms, it's a remarkable connection between the most extreme events in the cosmos and the everyday materials we use. The universe recycles everything, and neutron star mergers are part of that cycle, enriching the cosmos with elements that couldn't form any other way. The stardust that builds new worlds. The material ejected from neutron star mergers doesn't disappear. It spreads through space, mixing with interstellar gas and dust. Over time, this enriched material collapses to form new stars and planets. The stardust that builds new worlds includes the heavy elements from neutron star collisions, the carbon and oxygen from stellar winds, the iron from supernovae. Every element heavier than hydrogen and helium was created in stars or stellar collisions. We're made of stardust. That's not poetic exaggeration. It's literal truth. The atoms in your body, carbon, nitrogen, oxygen, calcium, iron, were forged in stars, some in the cores of massive stars, some in supernovae, some in neutron star mergers. These atoms were scattered into space, drifted for millions or billions of years, eventually becoming part of the molecular cloud that formed our solar system. The stardust built Earth, built you, built everything around you. Neutron star mergers are part of that story, contributors to the cosmic recycling that makes life possible. The merging of space and time. When neutron stars merge, they don't just collide in space, they merge space and time. Space-time itself is twisted, distorted, reshaped by the extreme masses and accelerations involved. Gravitational waves are literal ripples in space-time, compressions and stretches in the fabric of the universe. Near the merger, space-time is so warped that clocks run at different rates, distances change, light bends in extreme ways. The merging of space and time is predicted by general relativity, and neutron star collisions are among the best laboratories for testing these predictions. The gravitational waves from the 2017 merger matched theoretical predictions with remarkable accuracy, confirming Einstein's century-old theory in a regime of extreme gravity. But there are still mysteries. What happens at the exact moment of merger? How does matter behave when compressed beyond neutron degeneracy pressure? These questions push the boundaries of physics, requiring both observation and theory to unravel. The ripples that reach the Earth. On August 17, 2017, gravitational waves from a neutron star merger reached Earth. They'd been traveling for 130 million years, crossing the universe at the speed of light. LIGO's detectors in Louisiana and Washington felt the ripples first, followed by Virgo in Italy. The signal lasted about 100 seconds, sweeping up in frequency as the stars spiraled together. The ripples that reached the Earth were tiny. They stretched and compressed the detector's arms by less than the diameter of a proton, but they were measurable, and they carried information. About 2 seconds after the gravitational wave signal ended, telescopes detected a gamma-ray burst from the same direction. This was the first time gravitational waves and light had been observed from the same event, a historic moment for astronomy. Within hours, telescopes around the world turned toward the source, observing the kilonova as it brightened and faded. The ripples that reached Earth opened a new era in astronomy, proving that multi-messenger observations could reveal the universe's secrets in unprecedented detail. The discovery of gravitational waves in 2017. The 2017 detection was momentous. It was the first time gravitational waves from neutron stars had been observed, and the first time a gravitational wave event had been seen in light as well. This multi-messenger observation allowed astronomers to study the event from every angle. They measured the masses of the merging stars, estimated their distance, tracked the evolution of the kilonova, and detected the heavy elements in the expanding debris. The discovery of gravitational waves in 2017 confirmed long-standing theories about neutron star mergers, about kilonova production, about the origin of heavy elements. It also opened new questions. How common are these mergers? Do they all produce similar kilonova? What happens to the remnant? Does it become a massive neutron star or collapse into a black hole? These questions are now being pursued with more sensitive detectors and larger telescope networks, building on the foundation laid by that historic August day. The confirmation of Einstein's predictions. Einstein's general relativity, published in 1915, predicted gravitational waves as a consequence of accelerating masses, distorting space-time. For decades, this remained a theoretical prediction, impossible to test directly. Indirect evidence came in the 1970s from the Hulse-Taylor binary pulsar, which was observed to be losing orbital energy at precisely the rate predicted if it were emitting gravitational waves. But direct detection required technology that didn't exist until the 21st century. LIGO's first detection in 2015 confirmed Einstein's predictions for black hole mergers. The 2017 neutron star merger provided further confirmation in a different regime with different physics. The confirmation of Einstein's predictions is ongoing. Every new gravitational wave detection tests general relativity in slightly different conditions. So far, Einstein's theory has passed every test with flying colors. But physicists continue to look for deviations, for hints that general relativity might need modification at extreme scales. Neutron stars and their mergers are crucial testing grounds for these deep questions. The cosmic symphony we can now hear, gravitational wave astronomy, has been called listening to the universe. Where traditional astronomy is visual, we see light from distant objects. Gravitational wave astronomy is auditory in nature. We hear the universe's vibrations, the ripples in space-time translated into sound by our detectors. The cosmic symphony we can now hear includes the chirps of merging black holes, the longer sweeps of neutron star sporals, and potentially the hum of background gravitational waves from the early universe. Each event has its own signature, its own sound. A neutron star merger sounds different from a black hole merger. The waves sweep through lower frequencies. The signal lasts longer. By listening to these cosmic sounds, we learn about the objects that create them, about their masses, spins, and internal structure. It's a new sense, a new way of experiencing the universe, and we're just beginning to explore what we can hear. The bright flashes of gamma rays. Many neutron star events are accompanied by gamma rays, the highest energy photons in the universe. Gamma ray bursts, or GRBs, are among the most energetic events known, and some are associated with neutron star mergers. When the 2017 merger was detected in gravitational waves, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same location just 1.7 seconds later. The bright flashes of gamma rays are thought to be produced by jets of material launched at relativistic speeds from the merger site. These jets pierce through the surrounding debris, and if they're pointed toward Earth, we see a brilliant flash of gamma rays. Not all neutron star mergers produce detectable GRBs. It depends on the jet's orientation, but when we do see them, they're powerful tools for locating and studying these events. Gamma rays travel at light speed, so they arrive around the same time as gravitational waves, making them ideal for multi-messenger astronomy. The connection between pulsars and GRBs. For years, astronomers debated the origins of gamma ray bursts. Some GRBs are clearly associated with supernovae, the explosions that create neutron stars. These are long-duration GRBs, lasting more than 2 seconds. But short-duration GRBs, lasting less than 2 seconds, had a different origin. The 2017 multi-messenger event confirmed that at least some short GRBs come from neutron star mergers. The connection between pulsars and GRBs is complex. Young neutron stars, freshly formed in supernovae, can produce GRBs through jets. Merging neutron stars produce short GRBs, and magnetars, with their powerful magnetic fields, might produce some of the mysterious fast radio bursts that pulse across the universe. The connection isn't always direct, but neutron stars in various forms are central to many of the universe's most energetic transient events. Understanding these connections helps astronomers piece together the life cycles of stars and the processes that shape the high-energy universe. The theories of what lies inside. What's inside a neutron star? It's one of the great unknowns in physics. We know the outer layers are a solid crust of neutron-rich nuclei. Below that, the neutrons become more concentrated, eventually forming a superfluid. But deeper still, the conditions are so extreme that standard nuclear physics may not apply. The theories of what lies inside include several possibilities. Perhaps the core is just neutrons, packed as tightly as possible. Or perhaps the neutrons break down into their constituent quarks, forming quark matter. There might be exotic particles, hyperons containing strange quarks, or even stranger forms of matter that we've never imagined. The exact state depends on the equation of state, the relationship between pressure and density at these extreme conditions. Different equations of state predict different maximum masses for neutron stars. By measuring neutron star masses and radii, astronomers constrain these theories, narrowing down what's possible inside these mysterious objects. The possibility of quark matter. Deep inside the most massive neutron stars, the pressure might be so high that neutrons themselves break down. Neutrons are made of quarks, up quarks and down quarks, bound together by the strong force. Under extreme pressure, it's possible that neutrons dissolve into a sea of free quarks. This quark matter would behave differently from ordinary nuclear matter, with different pressure and density relationships. The possibility of quark matter is real but unconfirmed. If it exists, it would be found only in the cores of the most massive neutron stars, in a region we can never directly observe. But its presence would affect the star's properties, its maximum mass, its radius, how it responds to tidal forces during a merger. By studying these observable properties, astronomers can infer whether quark matter exists. Some theories even suggest that entire stars could be made of quark matter. Strange stars, objects that are even denser than neutron stars. These remain theoretical, but they're not impossible. The sea of neutrons and exotic particles. Inside a neutron star, there might be more than just neutrons. At high densities, other particles can become stable that wouldn't exist in normal matter. Hyperons, particles containing strange quarks, might form delta baryons. Excited states of protons and neutrons could appear. There might even be kaons, or pions, particles usually seen only in high-energy collisions. The sea of neutrons and exotic particles is a quantum soup, governed by rules we're still learning. Each particle type affects the star's equation of state, changing how matter responds to pressure. Some exotic particles soften the equation of state, allowing more compression, which would lower the maximum mass of neutron stars. Others might stiffen it. Observational constraints from neutron star masses help rule out some possibilities, but there's still uncertainty. The interiors of neutron stars remain one of physics' great frontiers, a place where we test our understanding of matter at its most fundamental level, the superfluid core that flows without friction. Below the solid crust, neutrons in a neutron star form a superfluid, a state of matter that flows without viscosity, without friction. This happens when neutrons pair up at the quantum level, similar to how electrons pair in superconductors. The superfluid core that flows without friction has strange properties. It can support persistent currents that never decay. It can rotate at a different rate than the crust, leading to phenomena like glitches when the two briefly couple and exchange angular momentum. Superfluidity is a quantum phenomenon, usually seen only in laboratory experiments with liquid helium, cooled to near absolute zero. But in neutron stars, the extreme density creates conditions where superfluidity emerges naturally. Despite temperatures of millions of degrees, the superfluid core is invisible to us, but its effects are observable. Glitches in pulsar timing, the cooling rate of neutron stars, both are influenced by the superfluid interior, giving us indirect evidence of this exotic state of matter. The neutron drip line within. In the outer crust of a neutron star, there's a boundary called the neutron drip line. Above this line, atomic nuclei exist in a lattice, but they're extremely neutron-rich, far more than any stable atom on Earth. Below this line, the neutrons begin to drip out of the nuclei, forming a gas of free neutrons coexisting with neutron-rich nuclei. Deeper still, the nuclei dissolve entirely, and it's just neutrons. The neutron drip line within marks a transition, a layer in the star's structure where matter changes character. This region is exotic, with nuclei in shapes and configurations that don't exist anywhere else. Simulations suggest strange nuclear structures, rods, sheets, tubes, collectively called nuclear pasta because of their shapes. These structures affect how the crust responds to stress, how heat is conducted, how matter moves during a starquake. The neutron drip line is one of many layers in a neutron star's complex internal structure, each layer with unique physics, each contributing to the star's overall behavior. The equations that describe impossible matter. Describing neutron star matter requires pushing the equations of physics to their limits. The equation of state relates pressure, density, and temperature for matter under extreme conditions. For neutron stars, we need an equation of state that works at densities several times that of atomic nuclei. But we can't test these densities in laboratories. We have to rely on theory, quantum chromodynamics, nuclear physics, many-body quantum mechanics. The equations that describe impossible matter are complex and uncertain. Different theoretical approaches give different results. Some predict stiffer matter that resists compression, supporting more massive stars. Others predict softer matter that compresses more easily, limiting maximum mass. Observations of neutron stars, their masses, radii, how they behave during mergers, help constrain these equations. It's a back and forth between theory and observation, slowly narrowing the possibilities, converging on a better understanding of how matter behaves in conditions we can never create on Earth. The mystery of the star's maximum mass. How massive can a neutron star be? There's a limit, determined by the equation of state. Too much mass, and gravity overcomes neutron degeneracy pressure, collapsing the star into a black hole. Current observations suggest the maximum is around 2 to 2.5 solar masses, but the exact value is uncertain. The mystery of the star's maximum mass is tied directly to the physics of dense matter. A stiffer equation of state allows higher masses. A softer one limits them. By measuring the masses of the heaviest neutron stars, astronomers constrain the equation of state. The current record holder is PSR J0740 plus 6620, with a mass of about 2.08 solar masses. Neutron star mergers also provide information. If the remnant survives as a neutron star, rather than immediately collapsing, it tells us the maximum mass is at least as high as the remnant's mass. Solving this mystery will tell us not just about neutron stars, but about the fundamental nature of matter. The border between neutron stars and black holes. There's a narrow range between about 2 and 3 solar masses where the boundary lies. Below this, a collapsing core stabilizes as a neutron star. Above it, nothing can stop gravity. The collapse continues, forming a black hole. The border between neutron stars and black holes is one of the sharpest transitions in nature. On one side, you have an object with a surface, with matter in a definable state, with light escaping. On the other, an event horizon, a point of no return, a singularity. Add a little more mass to the maximum mass neutron star, and it collapses. The border is determined by the equation of state, and finding it precisely is a major goal of astrophysics. Observing objects near this boundary, either the most massive neutron stars or the least massive black holes, helps pinpoint where the transition occurs. It's a fundamental dividing line in the universe, separating two radically different fates for stellar cores. The tipping point of collapse. What triggers the collapse? For a stable neutron star, it's often accretion. If a neutron star in a binary system gains mass from its companion, it can exceed the maximum mass and collapse into a black hole. Or if two neutron stars merge and the combined mass is too high, the remnant collapses. The tipping point of collapse is precise. One moment, you have a neutron star. The next, a black hole. The transition is nearly instantaneous on human timescales. Though the dynamics are complex, the star doesn't simply wink out. There's a brief period where the remnant might be supported by differential rotation or thermal pressure before finally collapsing. Some mergers produce a hypermassive neutron star that survives for seconds or minutes before collapsing. Others collapse immediately. Understanding the tipping point helps astronomers predict the outcomes of mergers and constrain the properties of dense matter. It's a critical threshold in stellar evolution. The equation of state that astronomers chase. The equation of state is holy grail for neutron star researchers. Get it right, and you understand dense matter. You can predict neutron star maximum masses, radii, cooling rates, merger outcomes, but determining it is challenging. It requires combining nuclear theory, quantum physics, and astronomical observations. The equation of state that astronomers chase is constrained from multiple directions. Lab experiments with heavy ion collisions probe nuclear matter at high densities, though not as high as neutron star cores. Observations of neutron star masses provide upper limits. The equation of state must support at least the heaviest observed star. Measurements of radii from X-ray observations and gravitational wave signals provide additional constraints. Cooling rates tell us about internal composition. Slowly, these constraints are narrowing the possibilities. The equation of state is coming into focus, though uncertainties remain. Each new observation adds a piece to the puzzle, bringing us closer to understanding the nature of the densest matter in the universe. The observations from NICER on the ISS. NICER, the Neutron Star Interior Composition Explorer, is an X-ray telescope mounted on the International Space Station. It observes pulsars, measuring the arrival times of X-ray pulses with exquisite precision. The observations from NICER on the ISS are designed to measure neutron star radii. As a pulsar rotates, hot spots on its surface sweep in and out of view. The pattern of X-ray pulsations depends on the star's size and shape. By modeling these pulse profiles, astronomers can determine the star's radius. Combined with mass measurements, this constrains the equation of state. NICER has observed several pulsars, providing the most precise radius measurements to date. The results suggest radii of about 12 to 13 kilometers for typical neutron stars, slightly larger than some predictions. These measurements are crucial inputs for understanding dense matter physics. NICER represents a new generation of instruments, purpose-built to probe neutron star properties with unprecedented precision. The mapping of a star smaller than a city. Mapping the surface of a neutron star seems impossible. Its tiny, distant, and we can't resolve it with traditional imaging. But pulsar timing allows a form of mapping as hot spots rotate in and out of view. The X-ray brightness varies. The details of this variation, the pulse shape, the timing, how it changes with energy, encode information about the star's surface temperature distribution, its shape, its magnetic field geometry. The mapping of a star smaller than a city is indirect but powerful. By fitting models to the observed pulse profiles, astronomers reconstruct the surface properties. They find that neutron stars aren't perfectly spherical. Rapid rotation flattens them slightly. The hot spots aren't always at the magnetic poles. The surface temperature varies, with some regions hotter than others. This mapping reveals details about the star's magnetic field, its thermal evolution, and even hints about its interior structure. It's astronomy at its most sophisticated, extracting maximum information from minimal data. The pulse profiles that reveal its shape. Each pulsar has a unique pulse profile, the shape of its brightness variation over one rotation. Some have single peaks, others have double peaks. Some are narrow, others broad. These pulse profiles that reveal the star's shape are determined by several factors: the star's rotation rate, its magnetic field geometry, the viewing angle from Earth, and importantly, its shape. General relativity predicts that rapid rotation should flatten a neutron star into an oblate spheroid. This flattening affects how light rays bend around the star, changing the pulse profile. By carefully modeling the profiles observed by NICER and other instruments, astronomers can measure this flattening and determine the star's shape. The results confirm that millisecond pulsars are indeed flattened, as predicted. The amount of flattening depends on the star's moment of inertia, which in turn depends on how mass is distributed inside. Another constraint on the equation of state: the slight flattening from rapid rotation. A neutron star spinning hundreds of times per second experiences enormous centrifugal forces. These forces try to fling material outward, working against gravity's inward pull. The result is a slight flattening, turning the star from a perfect sphere into an oblate spheroid, wider at the equator than at the poles. The slight flattening from rapid rotation is just a few percent, but it's measurable through its effects on pulse profiles and gravitational wave emission. A perfectly spherical spinning star wouldn't emit gravitational waves unless its mass distribution is asymmetric. But a flattened star can have a small mountain or asymmetry that does produce waves. Astronomers search for continuous gravitational waves from spinning neutron stars, signals that would tell us about the star's shape and interior. So far, these haven't been detected, but improving sensitivity may change that. The flattening also affects how the star responds during a merger, influencing the gravitational wave signal and the outcome. The moment of inertia that defies intuition. The moment of inertia describes how mass is distributed in a rotating object. For a neutron star, it's a critical property, but it's not intuitive because matter inside is compressed to such high densities, and because relativistic effects are strong. The moment of inertia doesn't follow simple formulas. The moment of inertia that defies intuition is smaller than you'd expect for an object with the star's mass and radius, because so much mass is concentrated near the center. Measuring it provides direct information about the star's internal structure. One way to measure it is through binary pulsars. The gravitational interaction between the pulsar and its companion causes precession of the orbit, and the rate depends on the pulsar's moment of inertia. Another way is through gravitational waves during a merger. The tidal deformability, which is related to the moment of inertia, affects the waveform. These measurements are difficult but incredibly valuable, offering direct probes of what lies inside these mysterious stars. The starquakes that shake the cosmos. Neutron stars experience starquakes, sudden readjustments of their crusts, as a pulsar spins down, losing rotational energy over time. the centrifugal force decreases. The star slowly becomes more spherical, but the solid crust can't adjust smoothly. It builds up stress, like tectonic plates on Earth. Eventually, the stress exceeds the crust's strength, and it cracks. The crust suddenly shifts to a new configuration, releasing energy. The starquakes that shake the cosmos are detected as glitches in pulsar timing. The pulsar suddenly spins up slightly, increasing its rotation rate by a tiny fraction. Then it gradually relaxes, spinning down again over weeks or months. These glitches tell us about the star's interior, how the superfluid core couples to the crust, how strong the crust is, how stress accumulates and releases. Starquakes are rare, but well documented, particularly in young pulsars like the Vela pulsar, which glitches regularly, providing a natural laboratory for studying neutron star physics. The sudden jumps in pulsar speed. When a glitch occurs, the pulsar's rotation rate jumps suddenly. In a fraction of a second, the period decreases. The star spins faster. The sudden jumps in pulsar speed are small, typically 1 part in a million or less, but they're measurable with precise timing. Following a glitch, the pulsar doesn't immediately return to its pre-glitch behavior. There's a relaxation phase, where the rotation gradually returns toward the long-term spin-down trend. This relaxation reveals interactions between the crust and the superfluid interior. The superfluid rotates faster than the crust initially, and angular momentum is gradually transferred until they recouple. Different glitches show different relaxation behaviors, suggesting that the interior structure varies between pulsars, or that different types of glitches involve different mechanisms. Studying these jumps provides one of the few ways to probe what's happening inside a neutron star, hidden beneath kilometers of ultra-dense crust. The glitches that reveal their interiors. Glitches are windows into neutron star interiors. Each glitch provides data about how the star's components interact. The solid crust, the superfluid neutrons, possibly the superfluid protons, if they exist. The glitches that reveal their interiors are clues in a cosmic detective story. Why do some pulsars glitch frequently, while others never do? Why do glitches vary in size? What triggers them? The answers lie in the star's internal structure, in the strength of coupling between the superfluid and the crust, in the distribution of angular momentum. By cataloging glitches across many pulsars, astronomers identify patterns. Young pulsars glitch more often. Larger glitches tend to be followed by longer relaxation times. These patterns constrain theoretical models of neutron star interiors, helping narrow down the possible states of matter inside. It's indirect evidence, but it's some of the best we have for understanding what happens in the hidden cores of these stars. The magnetic fields that decay over time. Neutron star magnetic fields aren't permanent. They decay over millions of years. Young pulsars have stronger fields, typically around 1 trillion Gauss. Old pulsars have weaker fields, perhaps billions of Gauss or less. The magnetic fields that decay over time do so through several processes. Ohmic decay, where electric currents in the star's crust gradually dissipate, releasing energy as heat. Hall drift, where the magnetic field evolves under its own dynamics, migrating through the star. And ambipolar diffusion, relevant in the core, where charged and neutral particles move at different rates. This decay affects the pulsar's evolution. As the magnetic field weakens, the torque on the star decreases, and the spin-down rate changes. Eventually, the pulsar becomes too weak to generate detectable radio emission. It dies as a pulsar, though the neutron star itself persists. Understanding magnetic field decay helps astronomers estimate pulsar ages and lifetimes, and it's crucial for modeling the pulsar population in the galaxy. The slow death of the pulsar signal. Every pulsar eventually goes silent. As the star spins down and its magnetic field decays, the conditions that generate radio emission cease. The slow death of the pulsar signal takes millions of years. Young pulsars are bright, spinning fast, with strong fields. They're easy to detect. Old pulsars are dim, spinning slowly, with weak fields. Many are below the detection threshold of current telescopes. Eventually, a pulsar crosses the death line, a threshold in period and magnetic field strength below which radio emission stops. The star becomes a quiet neutron star, still there, still dense, still spinning, but no longer broadcasting radio pulses. These dead pulsars vastly outnumber active ones. Estimates suggest there are hundreds of millions of neutron stars in our galaxy, but only tens of thousands of active pulsars. The rest have fallen silent, invisible, except through other means, accretion, if they have a companion, or X-rays if they're still hot enough to glow. The cooling neutron stars and X-ray light. Even after a neutron star stops pulsing, it can still be visible. If it's young enough, it's still hot, glowing in X-rays as it slowly cools. The cooling neutron stars and X-ray light are targets for observatories like Chandra and XMM Newton. By measuring their temperatures and how they change over time, astronomers learn about the star's interior. Cooling depends on what's inside. If the core contains exotic particles or superfluids, the cooling rate differs from a simple neutron core. Some processes, like neutrino emission from specific reactions, can dramatically accelerate cooling. By comparing observed cooling curves to theoretical predictions, astronomers constrain the composition. It's another indirect probe of the interior, complementing other methods. And it's a slow process. Neutron stars remain hot for millions of years, gradually fading from brilliant X-ray sources to dim, cold objects, barely warmer than the cosmic background. The remnants found in supernova nebulae. Many neutron stars are found at the centers of supernova remnants, the expanding shells of gas ejected when the star exploded. These remnants glow in radio waves, optical light, and X-rays, powered by the energy of the explosion, and sometimes by the pulsar at their heart. The remnants found in supernova nebulae provide context for the neutron star's birth. By studying the remnants' expansion rate and chemical composition, astronomers determine when the supernova occurred and what kind of star exploded. The neutron star itself might be powering a pulsar wind nebula, a glowing cloud of high-energy particles energized by the pulsar's rotation. These nebulae are beautiful structures, often showing intricate filaments and jets. They're laboratories for studying particle acceleration, magnetic fields, and the interaction between a pulsar and its environment. Each remnant tells a story of a star's death, a neutron star's birth, and the ongoing transformation of stellar material into the building blocks of future generations. The Crab pulsar and its glowing cloud. The Crab Nebula is one of the most famous supernova remnants. It was created by a supernova observed in 1054 CE by Chinese and Arab astronomers. At its center lies the Crab pulsar, spinning 30 times per second, powering the nebula with a wind of high-energy particles. The Crab pulsar and its glowing cloud are iconic. The nebula shines across the spectrum, from radio to gamma rays, energized by the pulsar's rotational energy. The pulsar itself is young, less than 1,000 years old, and still spinning relatively fast. It's a benchmark object, studied intensely because it's bright and nearby. Observations of the Crab have revealed jets, rings, and a complex magnetic structure. The nebula's brightness varies over time, with occasional flares as magnetic reconnection events release bursts of energy. The Crab is a window into young neutron stars, showing us what they look like shortly after birth, still energetic, still shaping their surroundings. The Vela pulsar and its filament trails. The Vela pulsar is another well-studied object, located in the Vela supernova remnant, about 1,000 light-years away. It spins about 11 times per second and is known for its frequent glitches, sudden increases in rotation rate caused by starquakes. The Vela pulsar and its filament trails show a complex interaction between the pulsar wind and the surrounding nebula. The pulsar jets extend outward, creating elongated structures visible in X-rays. These jets are unstable, breaking up into knots and filaments as they interact with the ambient medium. The Vela pulsar is one of the brightest, persistent sources of gamma rays in the sky, making it a prime target for high-energy observatories. Its proximity and brightness have made it a key object for understanding pulsar physics, and its glitches, occurring every few years, provide regular opportunities to study neutron star interiors and the coupling between the crust and superfluid core, the mysterious central compact objects. Not all neutron stars are pulsars. Some, called central compact objects or CCOs, are found in supernova remnants, but don't pulse in radio waves. They're detected primarily in X-rays, glowing from their residual heat. The mysterious central compact objects are puzzling because they seem to have weak magnetic fields compared to typical pulsars, and they rotate slowly or not detectably at all. Why are they different? One theory is that they're young neutron stars whose magnetic fields are somehow hidden or buried beneath the surface. Another is that they represent a different evolutionary path, perhaps stars that formed with weaker fields to begin with. CCTOs challenge our understanding of neutron star diversity. They suggest that not all neutron stars follow the same trajectory. Some might never become radio pulsars. Others might have magnetic fields that decay exceptionally quickly. Studying CCOs helps astronomers understand the full range of neutron star properties and behaviors. The hidden stars with no pulses. Across the galaxy, there are neutron stars we've never detected. They don't pulse. They're not hot enough to glow brightly in X-rays. They don't have companions to accrete from. They're just there, dark and silent, invisible to current telescopes. The hidden stars, with no pulses, vastly outnumber the ones we've found. Estimates suggest there are hundreds of millions of neutron stars in the Milky Way, but we've detected only tens of thousands. The rest are dark, cooling slowly. Their radio emission long since ceased. Occasionally, one might reveal itself through gravitational lensing, bending the light of a background star, or through a chance encounter, passing close to a molecular cloud and creating a detectable disturbance, but most will remain hidden forever. Relics of ancient supernovae, monuments to stellar death scattered throughout the galaxy, unseen and unknowable. The ghostly soft gamma repeaters. Soft gamma repeaters, or SGRs, are a class of objects related to magnetars. They emit bursts of soft gamma rays and X-rays, sometimes repeatedly over short periods. The ghostly soft gamma repeaters are thought to be magnetars, undergoing magnetic field rearrangements similar to solar flares, but far more energetic. Between outbursts, SGRs can be quiet for years, barely detectable, then suddenly they erupt, emitting dozens or hundreds of bursts over days or weeks. The largest SGR flare ever recorded, from SGR 1806 to 20 in 2004, released more energy in a tenth of a second than the sun emits in 100,000 years. If it had occurred within a few light years of Earth, it could have caused significant damage to our atmosphere. Fortunately, it was 50,000 light years away. SGRs remind us of the immense energies contained in neutron star magnetic fields and the potential for sudden, violent releases. The magnetars that sleep and awaken. Magnetars aren't always active. They go through cycles, periods of intense activity, followed by years or decades of quiescence. The magnetars that sleep and awaken are unpredictable. A magnetar might emit thousands of X-ray bursts in a single outburst, then fall silent. Years later, it might erupt again. What triggers these awakenings? The current theory is that the ultra-strong magnetic field stresses the star's crust. Over time, stress builds until the crust cracks, triggering a starquake and a burst of activity. Magnetic field lines rearrange, reconnecting in violent events that release enormous energy. Eventually, the field settles into a new configuration, and the magnetar returns to sleep. Understanding these cycles helps astronomers predict when magnetars might become active, though the exact timing remains uncertain. Each outburst is an opportunity to study these extreme objects and the physics of ultra-strong magnetic fields. The theories of strange stars. What if neutron stars aren't made of neutrons? What if, under extreme pressure, matter transitions entirely into strange quark matter? This is the theory of strange stars. Objects where the entire star, not just the core, is composed of quarks. The theories of strange stars suggest these objects would be slightly smaller and denser than neutron stars, with different properties. They'd have no solid crust, just a thin layer of normal matter over a quark liquid. Their maximum mass might be higher, and they'd cool differently, potentially explaining some anomalous observations. Strange stars remain theoretical. We have no confirmed examples, but they're not ruled out. Some neutron stars could actually be strange stars, and we wouldn't necessarily know from current observations. Future measurements of radii, masses, and cooling curves might distinguish between neutron stars and strange stars, testing whether this exotic form of matter exists in nature. The possibility of quark stars. Quark stars are similar to strange stars, but might represent a different configuration. Instead of transitioning smoothly from neutron matter to quark matter, a quark star might have a sharp boundary between phases. The possibility of quark stars adds another layer to the diversity of compact objects. They might form from neutron stars through a phase transition, triggered by cooling or accretion, or they might form directly in supernovae under specific conditions. Some astronomers have suggested that certain observed objects, with properties that seem inconsistent with standard neutron stars, might be quark stars, but the evidence remains ambiguous. Distinguishing quark stars from neutron stars requires precise measurements of mass, radius, and internal structure. The same measurements that constrain the equation of state. If quark stars exist, they represent a fundamentally different form of matter, stable at macroscopic scales, a new state in the universe's catalog of possibilities. The search for the densest matter in nature. Neutron stars are our best laboratories for studying the densest matter in nature. At their cores, densities exceed that of atomic nuclei, reaching several times nuclear density. Nothing denser exists, except inside black holes, where our physics breaks down entirely. The search for understanding this matter drives much of neutron star research. What happens to atoms at these densities? What particles exist? What forces dominate? These aren't just academic questions. They're fundamental to understanding how matter behaves, how the universe works at the smallest scales. The densest matter in nature tests our theories of quantum chromodynamics, the strong force, nuclear physics. It might reveal new particles, new phases of matter, new physics we haven't imagined. And neutron stars, scattered throughout the galaxy, are natural experiments running continuously, showing us what's possible when matter is pushed to its absolute limits. The role of neutron stars in the universe. Neutron stars play several roles in the cosmic story. They're the remnants of massive stars, endpoints of stellar evolution. They're sources of heavy elements, forging gold and platinum in their collisions. They're laboratories for extreme physics, testing our theories at conditions we can't replicate. They're cosmic clocks, their pulses more regular than any human-made timepiece, and they're sources of gravitational waves, rippling space-time as they spiral together. The role of neutron stars in the universe is multifaceted. They shape supernova remnants, energizing nebulae with pulsar winds. They affect galaxy evolution through supernovae, distributing energy and heavy elements. They provide natural laboratories for studying matter, gravity, and magnetism in extreme regimes, and they connect to deep questions about the nature of matter, the limits of stability, the relationship between quantum mechanics and gravity. Neutron stars are small objects with enormous implications. The cosmic recycling of elements. The universe recycles everything. Hydrogen from the Big Bang forms stars. Stars fuse hydrogen into helium and heavier elements. They scatter this enriched material through stellar winds and explosions. The material mixes with interstellar gas, eventually forming new stars and planets. Neutron stars are crucial participants in this cycle. The cosmic recycling of elements depends on supernovae to distribute carbon, oxygen, silicon, and iron. It depends on neutron star mergers to create gold, platinum, and uranium. Without these processes, the universe would contain only hydrogen and helium. There would be no rocky planets, no complex chemistry, no life. Neutron stars, through their violent origins and occasional catastrophic collisions, enrich the cosmos. They're foundries, factories, producing elements that become part of everything: stars, planets, and perhaps living beings. The cycle continues, endlessly, throughout cosmic time. The creation of gold, platinum, and uranium. Every gold ring, every platinum catalyst, every uranium fuel rod. The atoms came from neutron star mergers. The creation of gold, platinum, and uranium requires the rapid neutron capture process, where atomic nuclei absorb neutrons faster than they can decay. This happens in the intense neutron flux of a merger, where temperatures reach billions of degrees and neutron densities are incomprehensible. In seconds, light elements are built up into heavy ones, climbing the periodic table. The resulting atoms are radioactive, decaying and releasing energy, powering the kilonova. Over time, they settle into stable isotopes: gold manages at 197, platinum 195, uranium 238. These atoms are scattered into space, mixing with the interstellar medium. Billions of years later, they're incorporated into new solar systems. The gold in your jewelry was created in a neutron star merger, somewhere in the galaxy, sometime in the past. It's stardust, forged in the universe's most extreme events. The light we see from their mergers. When neutron stars merge, we see light across the spectrum. Gamma rays arrive first, a brief flash lasting seconds. Then comes the kilonova, brightening invisible and infrared light over hours, peaking after a day or two, then fading over weeks. And throughout, there are X-rays, radio waves, signatures in every wavelength. The light we see from their mergers tells a story. The gamma rays reveal the formation of jets. The early blue light shows the hot, expanding debris. The later red light indicates cooling and the decay of radioactive elements. X-rays trace shocked gas. Radio waves appear as the debris interacts with the surrounding medium. By combining observations across all wavelengths, astronomers reconstruct what happened, how the stars merged, what they ejected, what they became. Multi-wavelength astronomy transforms a brief cosmic event into a detailed narrative, revealing the physics of the universe's most energetic collisions. The data collected by LIGO and Virgo. LIGO and Virgo are gravitational wave detectors, massive instruments designed to measure the tiniest ripples in space-time. The data collected by LIGO and Virgo from neutron star mergers is extraordinary. The 2017 event, GW 170817, provided about 100 seconds of data as the stars spiraled together. From this signal, astronomers extracted the masses of both stars, their spins, their orbital dynamics, and the distance to the merger. They measured how the stars deformed under tidal forces, constraining the equation of state. They tracked the final moments before coalescence, capturing the gravitational chirp as the stars touched. This data is analyzed and reanalyzed, refined with better models, yielding new insights years after the initial detection. LIGO and Virgo continue observing, detecting more mergers, building a catalog. Each event adds to our understanding, and future detectors will be even more sensitive, hearing mergers from across the universe. The combined power of electromagnetic and gravity observations. Multi-messenger astronomy combines gravitational waves and light, providing more information than either alone. The combined power of electromagnetic and gravity observations transforms our understanding. Gravitational waves tell us about the masses, spins, and dynamics of the merging objects. Light tells us about the environment, the ejected material, the elements created. Together, they provide a complete picture. For GW 170817, gravitational waves pinpointed the time and location. Electromagnetic observations identified the host galaxy, measured the kilonova's properties, and tracked the evolution of the debris. Combined, they confirmed that neutron star mergers create heavy elements, that short gamma-ray bursts come from these mergers, and that gravitational wave theory is correct in this regime. Multi-messenger astronomy is the future. Every major observatory now coordinates with gravitational wave detectors, ready to swing into action when the next merger is detected. It's a new way of doing astronomy, combining information across messengers, across the spectrum. The connection to fast radio bursts. Fast radio bursts, or fairies, are mysterious pulses of radio waves, lasting just milliseconds. They arrive from distant galaxies, carrying enormous energies. For years, their origin was unknown, but recent evidence suggests at least some FRBs come from magnetars. In 2020, a magnetar in our galaxy, SGR 1935 plus 2154, emitted a burst of radio waves, coincident with an X-ray flare. The connection to fast radio bursts was established. Not all FRBs necessarily come from magnetars. There might be multiple mechanisms, but magnetars are now leading candidates, at least for some fraction. The ultra-strong magnetic fields, the sudden energy releases, the brief timescales, all fit with what we observe in FRBs. If magnetars produce FRBs, it connects neutron stars to one of the most puzzling phenomena in modern astronomy. It shows that these objects, even in their quiet moments, can produce bursts detectable across the universe. The sudden blasts from distant galaxies. FRBs are sudden, intense, and brief. They release as much energy in milliseconds as the sun emits in days. The sudden blasts from distant galaxies are challenging to study because they're unpredictable and short-lived. But radio telescope arrays are now scanning the sky continuously, catching FRBs as they occur. Some FRBs repeat, allowing follow-up observations. Others are one-off events. The repeating ones might come from magnetars, while the non-repeating ones could have different origins, perhaps merging neutron stars or collapsing massive stars. Each FRB carries information about the intervening medium, the gas and plasma it passed through on its journey. By analyzing the signal, astronomers can study the structure of distant galaxies and the intergalactic medium. FRBs are both a mystery and a tool, puzzles to solve and probes of the universe's large-scale structure. The hypothesis of magnetars behind FRBs. The magnetar hypothesis for FRBs suggests that magnetic field rearrangements or starquakes on magnetars produce brief, intense bursts of radio emission. The hypothesis is supported by the 2020 detection from SGR 1935 plus 2154, which was much weaker than extragalactic FRBs, but otherwise similar in character. If scaled up, magnetar bursts could explain FRBs. The mechanism might involve magnetic reconnection in the magnetosphere, releasing energy that accelerates particles and generates coherent radio emission. Or it could be related to the crustal oscillations that follow a starquake. The hypothesis of magnetars behind FRBs is testable. More detections from known magnetars would strengthen it. Finding FRBs associated with young supernova remnants would support it, and detecting FRBs from the same source repeatedly fits with magnetars, which can have multiple outbursts. The connection between neutron stars and FRBs is one of the exciting frontiers in astrophysics today. The quiet neutron stars between explosions. Most of the time, neutron stars are quiet, between glitches, between magnetar flares, between observable pulses. They simply exist. The quiet neutron stars between explosions are the majority. Old, cooling objects, no longer actively pulsing, or young ones in quiescent states. These stars are difficult to study because they're faint and unspectacular, but they're important. They represent most of the neutron star population. Understanding their properties, their distribution, their evolution helps complete the picture. Some might be detectable through their thermal emission, glowing faintly in X-rays. Others might reveal themselves through gravitational effects if they pass near other stars, and some will remain forever undetected, silent reminders that not all cosmic objects broadcast their presence. The quiet ones outnumber the loud ones by vast margins, a hidden population shaping the galaxy in subtle ways. The population hidden across the Milky Way. The Milky Way contains hundreds of millions of neutron stars, but we've detected only a tiny fraction. The population hidden across the Milky Way is vast. Most are old, their pulsars long dead. Some are young but beamed away from Earth, their radio signals never reaching us. Others are obscured by dust, their light absorbed before it can reach our telescopes. This hidden population is important for understanding stellar evolution, supernova rates, the history of star formation in the galaxy. By modeling the population, astronomers estimate how many neutron stars should exist and where they should be. Surveys search for them using radio telescopes, X-ray observatories, optical instruments. Each detection adds to the census, but the vast majority will remain hidden, their presence inferred statistically rather than observed directly. They're out there, scattered through the galaxy's disk and halo, silent witnesses to billions of years of stellar death. The journey of neutron star research. Neutron star research has come far since the 1960s, from theoretical predictions to pulsar discoveries to gravitational wave detections. The journey has spanned decades and involved thousands of scientists. The journey of neutron star research continues. Every new observation, every improved detector, every refined theory adds to our understanding. Early work focused on establishing that neutron stars exist and measuring basic properties, masses, rotation rates, magnetic fields. Later work probed their interiors, constrained the equation of state, studied glitches and cooling. Recent work has opened gravitational wave astronomy, multi-messenger observations, studies of magnetar flares and fast radio bursts. The journey is far from over. Future instruments will detect fainter, more distant neutron stars. They'll measure properties with unprecedented precision. They'll answer questions we're asking now and reveal mysteries we haven't imagined. Neutron star research is a testament to human curiosity and ingenuity, pushing the boundaries of knowledge. The human story of their discovery. Behind every scientific discovery are people. The human story of neutron star discovery is fascinating. Jocelyn Bell, Burnell's careful observation and persistence led to the first pulsar detection. Her work was overlooked for the Nobel Prize, a decision that sparked important conversations about recognition in science. Countless astronomers, theorists, engineers, and technicians have contributed since. The LIGO team's decades-long effort to detect gravitational waves, often facing skepticism, culminated in the 2015 detection. The global collaboration that observed GW 170817 involved thousands of scientists across dozens of institutions and countries. The human story reminds us that science is a collective endeavor built on collaboration, persistence, and the willingness to pursue questions even when answers seem impossibly distant. Neutron stars capture our imagination because they're extreme, exotic, almost magical in their properties. but they're studied by real people with determination, creativity, and passion for understanding the universe. The women who found the first pulsar. Jocelyn Bell Burnell was a 24-year-old graduate student when she discovered the first pulsar in 1967. She was analyzing data from a radio telescope she'd helped build, looking for quasars, when she noticed an unusual signal, regular pulses every 1.337 seconds. She didn't dismiss it. She investigated, confirmed it was real, found more. The women who found the first pulsar, Bell Burnell and others who contributed but are less remembered, deserve recognition. Bell Burnell's discovery was awarded the Nobel Prize in 1974, but it went to her advisor Anthony Hewish and the observatory director Martin Ryle. She was excluded, a controversial decision that remains debated. Bell Burnell has spoken gracefully about this, noting that as a student, she might not have been expected to win, but also acknowledging the systemic issues women faced in science. Her story is both inspiring and cautionary, a reminder to ensure all contributors receive proper recognition. The expanding field of extreme physics. Neutron stars exist at the intersection of multiple fields: nuclear physics, quantum mechanics, general relativity, plasma physics, astronomy. The expanding field of extreme physics they represent draws researchers from across disciplines. Nuclear physicists study how matter behaves at high densities. Particle physicists investigate what particles might exist in cores. Relativists test general relativity's predictions in strong gravity. Astronomers observe the stars, measuring properties and dynamics. The expanding field is growing rapidly. Gravitational wave detections have energized the community. Multi-messenger astronomy has opened new avenues. New instruments provide unprecedented data, and theoretical work continues to refine models, predict new phenomena, interpret observations. Neutron star research is vibrant, collaborative, and full of open questions. It's a field where young scientists can make major contributions, where the next discovery might come from an unexpected direction, where the boundaries of knowledge are actively being pushed outward. The questions that still remain, despite decades of research, major questions remain unanswered. What's the exact equation of state? What's inside the core? Neutrons, quarks, something else? What's the maximum mass? How do magnetic fields evolve? What triggers magnetar flares? Do strange stars exist? How common are neutron star mergers? The questions that still remain are what make the field exciting. Each one represents a frontier, an opportunity for discovery. Answering them requires better observations, more sensitive instruments, refined theories. Some questions might be answered soon. Better mass and radius measurements could nail down the equation of state. Others might take decades. Understanding magnetar triggers requires catching them in action and correlating observations with theory. And some questions might lead to new questions. As often happens in science, the answers will deepen our understanding of matter, gravity, and the universe's most extreme objects. The border between theory and mystery. Neutron stars exist at the border between theory and mystery. We understand much: their formation, their basic properties, their role in the universe. But mysteries remain. The interior composition is uncertain. The maximum mass is debated. Magnetar behavior is unpredictable. Some objects don't fit our categories. The border between theory and mystery is where science happens. Theories make predictions. Observations test them. Sometimes observations confirm theories, pushing back the mystery. Sometimes observations reveal new puzzles, expanding the unknown. Neutron stars are perfect objects for this dance because they're accessible enough to observe, but extreme enough to challenge our understanding. They're laboratories where theory meets reality, where our best models are tested against nature's experiments. And at that border, discoveries happen. New physics, new phenomena, new insights into how the universe works, the legacy of stars that never truly die. Massive stars die spectacularly, but their cores persist. The legacy of stars that never truly die is written in neutron stars scattered throughout the galaxy. These cores are monuments to stellar death, reminders that even the most violent ends can produce something new. They're also functional objects, continuing to influence their environments through gravity, magnetic fields, and occasional outbursts. The legacy extends beyond the stars themselves. The heavy elements they create, scattered through supernovae and mergers, become part of future generations. The gravitational waves they emit, when they collide, carry information across the universe. The physics they reveal, through their existence at extremes, advances human understanding. Neutron stars embody transformation, from massive stars to compact remnants, from death to a new form of existence. They remind us that endings are also beginnings, that the universe wastes nothing, that even stellar death contributes to the ongoing cosmic story. The endless heartbeat of the universe. Pulsars tick with extraordinary regularity, their pulses arriving like a cosmic heartbeat. The endless heartbeat of the universe, embodied in these rotating stars, is one of the most poetic aspects of neutron star astronomy. It's a reminder of order in chaos, of regularity emerging from violence. Each pulse is a photon reaching across space, carrying information, marking time, and there are thousands of these heartbeats, scattered throughout the galaxy, each with its own rhythm. Some beat fast, hundreds of times per second. Others beat slowly, once every few seconds. Together they create a symphony, a cosmic percussion section, keeping time on the grandest scale. The heartbeat will continue long after human civilization has ended, long after the sun has died. Neutron stars will keep spinning, keep pulsing, keep marking time until the stars themselves fade away. Trillions of years from now, they're the universe's timekeepers, eternal witnesses to cosmic history, beating on through the ages.